Hello everyone. So we're going to move into unit number 2. So unit number 2 also consists with three sections. We are planning to do the per section today. So under per section, I'm planning to discuss about work, energy principle, or energy conservation, and then we will move into the momentum, and then we will discuss about momentum conservation and collision. So those will be the conceptual topics that we're going to discuss in this section. If you go to your Blackboard page, you see that we're going to work with the chapter number 7 and 8 together. Again, we're going to compress the material and learn conceptually. Okay, so now let's move into the presentation. Okay, so first thing we're going to discuss is the work done. In scientific sense, the work done has a actually very specific meaning. So simple example that you can think, work you use in many places. Somebody will say, I am doing homework, right? And somebody will say, I am working today. So you using the work wording in many places. But in physics, work has a very specific meaning. That means work is represent a measurable change in the system by because of the applied force. That is, we call it as the work done. So you can see it from these two pictures. The person is pushing the wall in the first diagram. You see it in here. So nothing changed in this case. Although you push the wall or you just standing there, nothing happened to the wall. It is staying the same, right? But in the second case, if you push the wall, if there is a deformation or something happened to the system or the wall in this case, we call it as this person is doing a work. So first case, no work. And the second case, it does the work. That's the difference between the work that you usually use in real life and the work done we are using in physics. Okay. So now work done basically can be defined by using force and the distance that object move because of the force, right? So simple example, if I have the object that will move after apply some force, we'll say I will going to start with applying 1 Newton force to this object. Then this is where it was earlier, initial position, right? After I applied 1 Newton, this object going to move 1 meter distance. Now the object is at this place. So now we call it as I do the work, how much I did, 1 Newton times 1 meter. So that will be the work done that will be measured by using Newton meters, because 1 Newton times 1 meter equal 1 joule. So that means Newton meter is the units for the work done. That whole set, we call it as the joule. So 1 joule equal 1 Newton meter. So now joule is again the scientist name coming from. So Newton meter, we call it as the 1 joule. Okay, so now this is in simple example. If I have the pawn, if I push with some force, if my pawn moves some distance, then there is a work done. If I push the pawn, if it is not moving, then there is no work done. Okay, that's the definition of the work done. Okay, so now work done will be able to calculate. We usually use the W letter for the work done to represent it. Work done will be able to calculate by using force times distance the object moved times the cosine of theta. So cosine of theta is the basically angle between, we'll say I drag this object in this way by applying the force, right? So now, I'm sorry. Now, how to calculate the work done will be this force. You going to times with the d distance it travel after I drag it, and take the angle between that two of cosine of that angle, we call it as the work done. You have the formula in here. That's the definition of the work done. When I see this equation, you should know what will happen when theta equals 0 and what will happen when theta equals 90 degrees, right? So when theta equals 0, that means cosine of 0. That is what? That is 1. So that means when I drag the object on the floor without any angle on the floor horizontal line, that will be the maximum work done, because then cosine of theta going to be 1. Because of that, your work done will be going to f times the distance, right? But when theta is 90 degrees, that means if I try to pull the object exactly in vertical direction, what I mean by in this way, if I drag the object in that way, since my object move into the right direction, there is no work done I have done. So cosine of theta in this case will be 0, because of that work done will be 0. There is a specific meaning. That means if pose and distance are in same direction, what that means is here, if F and D are same or opposite direction, same or opposite direction, that's what the theta 0 means, then your work done will be max. If pose and distance are perpendicular to each other, then there is no work done. Okay, so this means perpendicular to each other. Perpendicular to each other. If they are perpendicular to each other, there is no work done. So that's the basically meaning of the work done. So now work done is a scalar quantity, right? Scalar quantity. So that means there is no direction for the work done. But work done will be positive or negative. The reason is if you have the pose to the direction of the object move, then my pose and direction of the motion will be the same direction. In that case, work done will be positive. But due to any reason, we'll say I'm going to move this object on the my hand, but I have a very rough hand, then this object has the friction, right, between object and the hand. So now when I push the object, this object is still moving this direction. Since my friction is opposite direction, now what will happen? Friction will do the negative work. Okay, because of that, your work done can be negative or positive. And in addition to that, definitely in your class, we are doing it conceptually. We're going to work with the work done for constant force, but in real life, you know that your forces keep changing with the time, then you are not able to use this equation directly. There should be some modification for that. Okay. Okay, so now, as I mentioned, work done can be a positive, it can be a negative, it can be 0. This everything is possible for the work done, but it is a scalar quantity, right? So first thing is you can see is the negative case in here. So you have object motion to the right, but since I have friction backward direction, friction will do a negative work done, right? And the other case that you can see is centripetal force. I know that I'm going to discuss this in last section in unit 2, but centripetal force is basically when there is an object moving on a circle, always there is a force toward the center. That is, we call it as centripetal force. So now in this case, since my object moving perpendicular to the centripetal force, now if I calculate the work done from the centripetal force will be 0. So no work done from the forces that are perpendicular to the motion of the object. Other thing you can see, force of gravity. Force of gravity, if you have an object on the table, there is a force of gravity, but your object is not moving in that direction, object is moving in horizontal direction, then force of gravity does not do any work in that case, that kind of example. Okay, and also other forces can do positive and negative work. Here I have the tension force, do the positive work, but force of gravity point in this way, that will do the negative work. Okay, so because of that, positive and negative work done is possible. To find the work done for the system, you need to add them all. Okay. Okay, let's move into the energy. So definition of energy is, we call it as ability to do work done. We can define it as the energy, right? So energy is measured by using exactly same unit as work. That means energy units also joules. Okay, so now energy is one of the most important quantity that you can say it is a conserved quantity. Conserved means it is not changing for isolated system, right? So now energy is measured by using joule. It is the ability to do the work. That means I should have energy to do work. That is the energy means. And energy is also a scalar quantity, and it is a conserved quantity. That's why we can stay in our this state, because we all conserve the whole energy of the system. And so now energy is important thing that will transfer from one point to another point. Maybe it will convert into different energy. So let's think type of energies first. Okay. So what are the energy forms that we have in real life? You are experiencing this all energy in your real life. So everybody know that we have energy due to the motion of the object, or due to the position of the object. To keep you on this on the earth, you have energy. So that is belong to a mechanical energy. When you move your car with some velocity, there is a energy of the motion that is belong to a mechanical energy that we're going to focus in your, at least for the first part of the class. Okay. And in addition to that, radiation energy, you know that we have microwaves, we have light waves, radio waves, X-rays, those all are electromagnetic waves that we're going to discuss in your second part of the class, but those belong to radiant energy, right? And then you can have nuclear energy because of the atomic structure, or atoms put together or they apart each other. Because of that, there is a nuclear energy. And there can be electrical energy, right? So because of the electricity, we are getting the energy. And solar energy, right? And heat energy, light energy. There are chemical energy. There are many, many forms of energies. What I mean by conservation, this whole energy is conserved, but they can transfer from one energy to another by keeping whole conservation together. So that's the meaning of the energy conservation. Okay, now we're going to move into actually mechanical energy. As you remember that, as I mentioned, mechanical energy is the part that we're going to discuss in here, mechanical energy. So I usually use short names for those. Mechanical energy, I use M and E. And mechanical energy, we're going to discuss under two categories. First category is the kinetic energy. And I definitely use K and E for that, right? And the second one is the potential energy. Sorry, so I want to move to that potential energy. And I will use P and E for that. So now under mechanical energy, there are two energies. Both are because of the motion and the position. So kinetic energy is the first one. So kinetic energy is defined it as the energy of the motion. That means there should be a mass in the movement with the velocity. That mass should have a kinetic energy. That energy we will be able to calculate by using half times mass time velocity to the power 2, right? So mass of the object times velocity power 2. It is very important that energy unit always joules. That means kinetic energy also measured by units of joule, right? And then m is should be in kilograms to get that unit, and velocity should be meters per second to get that unit. So make sure that you use correct unit during the calculation. So now it is very easy to think in this way. So I have a kangaroo. So 2 kilograms moving with 1 meters per second. Now how do I calculate the kinetic energy? 2 times 1 to the power 2 divided by 2, half times mass time velocity power 2. Then after you calculate it, you're going to have the answer as 1 joule, right? So now, due to my explanation, let's say I have a kangaroo mom. So mom has 4 kilograms. So now what will happen to your kinetic energy? When I double this one, without changing the other parts, I will double the kinetic energy, right? But my last example, I still have a son kangaroo. So kangaroo, but 2 kilogram, but what will happen to my velocity is double. But when the velocity double, my kinetic energy will not be double. Why? Because I have velocity power 2. Then I need to do 2 to the power 2. That will give you 4 times. Okay, so that's how the kinetic energy will change, right? And then potential energy. So next step. So potential energy actually divide into 2 parts we're going to discuss. This one we're going to discuss under 2 category. One we call it as gravitational potential energy. Gravitational, no, that not have a space. Potential energy is the first one that I'm going to talk. That means if I sitting on the chair, I have the potential energy. That potential energy because of the position of myself. So when there is an object in some height, I have a phone. If I have a table, with compared to this table, this phone has the potential energy, right? Because it is in some height. That is, we call it as the gravitational potential energy. So gravitational potential energy will be the energy of the position. So I will move into a little more about that in a minute. And second category that I have here is the spin potential energy. Second one, okay? So second one is the spin potential energy. So spin potential energy means because of the spin, that spin can store the energy by compressing or by stretching the spring, right? Spin is something like this, everybody know that. So you can compress it, you can release it, stretch it. Because of that, there is a potential energy stored in the spring that is called it as spin potential energy. Okay, let's see how we calculate these two things. So now first potential energy, gravitational potential energy. To keep an object in any height, we can calculate the potential energy by using this formula. Potential energy equal mg times height. Mg is force of gravity and h is the height that you're going to keep the object. So it is very important in potential energy, you need to define your potential energy zero position. What I means by potential energy, if I use this point as 0, then after h height, I have the potential energy equal force of gravity of that object times h. Okay, so now can this potential energy be negative? Yes. That means if you define the potential energy 0 here, and if your object is sitting somewhere here with the h depth, then the potential energy at this point will be negative mg and h. So this h is a vertical height. So that's very important. Okay, what is the g is? G is not gram in here. Everybody know that already, right? G is 9.80 meters second squared, as we discussed earlier. Okay, so now spring potential energy, when you compress or stretch the spring, there is a potential energy. That potential energy will be able to calculate by using K times x to the power 2 over 2. So K is spring constant and x, spring constant is some constant for given spring. Okay, so that depends on different parameters, but for the given spring, that is a constant. That is called it as spring constant. And also measured units for that is Newton divided by meter. And x is the displacement of the spring. So you know that in your pen, you have a spring inside. That's why when you push it, your tip is coming out. Then when you let it go, that will be a stretch. Right? Because of this compress and stretch, there is a distance that your spring can compress. You see that this is my equilibrium spring that is at rest. But when I push it, it compress some distance where it was in here, it will compress x distance. In this case, I release it, then my spring will have a little bit stretch. Right? So now, according to how much it will compress or stretch, that is the x distance, displacement, measured in meters. Then you will get the potential energy again from joules. Okay, but potential energy is possible to be a negative or a positive value depending on where you choose your potential energy 0. But kinetic energy will never be 0. Right? And also it is very important that spring potential energy will never be 0 either. Because, I mean, never be negative either, right? Because you see that K is a positive constant, X is positive or negative, it doesn't matter since we are squared of that now. Okay, so now summary. Mechanical energy divided into two parts. One is potential energy, one is kinetic energy. The kinetic energy will be able to calculate by using half mass velocity squared. That is a scalar quantity that will be a positive value always. Potential energy divided into two parts. One is the gravitational potential energy will be able to calculate by using mg and h, and that possible to be negative or positive depend on the height or the depth that you choose in your potential energy 0 point. And second one is the spring potential energy. Spring potential energy will be able to calculate by using spring constant times displacement power 2 divided by 2. This also a positive value always. Okay. Okay, so now I just need to give a very brief introduction in here about conservative forces, because I think it is good to know because since we are planning to move into the energy conservation, right? So conservative forces means basically forces which work done is independent of the path it will take. When I say that, conservative forces are the forces that have the work done, but that work done is independent of the path you took. Simple example is gravitational force. Force of gravity straight down, it is independent of the path that ball fall down. It is the force of gravity. But if you think about the friction, if you go from A to B by using different path, maybe you use the different roads or maybe use the grass, then your friction, since they have a different friction, then your that force is basically not a conservative force. Okay, so we're going to focus into energy conservation principle to the conservative forces in your class. Conservative means forces that does not depend on the path it will take, right? So for the conservative forces, we have work done is 0 always. When the work done for the conservative forces 0, then we can define, we can derive energy is a constant if you choose an isolated system. Any isolated system, that isolated means basically energy does not cross the boundary of that your system, and in that system energy is conserved. That means energy in every position that you are calculating in your system, or every time that you are calculating on the system, is staying a constant, right? So now that is called it as the energy conservation. It does not mean that energy cannot be transferred. Energy is transferred, always convert into different categories, but total energy is conserved. That's what it means. Okay. So energy conservation in words is total words in here. You can read it yourself. Okay. But I need to come back to the work done again after we discuss kinetic energy and potential energy. I will remind you that we discussed the work done by using this formula earlier. So now after we discuss the kinetic energy and potential energy, we will be able to write the work done also, because it can combine to the energy conservation. So now work done can be again defined by using change of kinetic energy. Change of something is, we discussed that. Change of something means final place minus initial place. If it is a change of velocity, that will be V final minus V initial. If it is a change of kinetic energy, that will be kinetic energy final minus kinetic energy initial, right? So now, in addition to that, work done also can be able to define it as negative change of potential energy. That means potential energy initial minus potential energy final. So that's where actually energy conservation coming from, because you see that if you add these two together, you definitely will get the zero work done. That is the energy conservation. Okay. Okay, so now let's talk about how we're going to use this energy conservation for simple problems. Let's think about this, how this kinetic energy and potential energy will work, right? So we'll say this person is lift a stone to the height h from the ground, right? So this is where the ground is. So now in the ground, I am to use potential energy is zero. That is in your convenient, you can define anywhere you want, but usually we use the potential energy zero on the ground to solve the problem easily, right? So now when I have object in this height, we know this object should have potential energy. How much is that? That is mg times the height that I have it here as h. But since I'm going to hold these things, there is no kinetic energy because no velocity, right? Because of that, you see that in my bar chart, there is no kinetic energy. Kinetic energy at zero, potential energy is mg times h, right? But let's move into the all the way bottom. So now this object going to be dropped. And then when you come to here, there is a velocity. Now what will happen? Since I define the potential energy zero, my bar chart potential energy is zero, but my kinetic energy change into some value, because since I have velocity of the object, there is a kinetic energy on this object. Now, if you think about the height of this bar chart, it's just for you to get an understanding. Whole potential energy that I have it in blue color all the way top will convert into red color bar line, that is kinetic energy. That means this mgh is convert into kinetic energy, but since we know energy is conserved, then your initial position energy should be equal to final position energy. The initial position energy will say I have potential energy initial plus kinetic energy initial should be equal to potential energy final plus kinetic energy final. So now where's the initial and final? Those are, this is your initial position that you're going to start. This is your final position, right? So now potential energy initial, we know it is mgh, and kinetic energy initial is zero because there is no velocity. You're going to drop it. But when it lands the ground, there is no potential energy, but there is a kinetic energy that is half m and velocity squared, right? So these two are equal to each other. That concept you can use to calculate the h if you want. If you know the other things, if you need to calculate the velocity, you still can use it, right? You see that energy conservation, m will be always cancelled out. Because of that, it is very easy to use. There is no directional information at all. Because of that, you will be easily able to use this energy conservation for the problems that you have done by using kinematics earlier, right? Because that's a kinematics test that you can use that one of the kinematics equation and solve the problem, but it will take longer. This one is simpler. Initial energy equal final energy, then equal them and find whatever unknown variable is. Okay. Okay, so this will be another problem that you can easily visualize your energy conservation. So I'm going to probably erase the things that I wrote it in here a little bit to clear it up. And so now in this example, also, you can see what happened when the car is on the top of the hill. There is kinetic energy is 0 because velocity is 0. Right? And then there is a potential energy because of this height. Potential energy will say it is 600,000 joules. Now, kinetic energy and potential energy is total energy. This will be your total energy. Now, when you go to the bottom all the way, so your kinetic energy now, the same value as potential energy initial, and potential energy will be 0 on the bottom, is still total will be the same. So in between cases also, you can see the same pattern in here, right? But there is a kinetic energy and also potential energy in the middle of the track, because you have velocity and the height both in each places. Okay, I hope you guys get an understanding about that. And now let's move into power. Power is basically work done per unit time. So that means work done per unit times means joule divided by second, right? Joule divided by second unit, we call it as watts. That's the units of the power. So now power is not the work done, but the work done per unit time is the power, right? So now you can think the person climbing a staircase by walking, and also we'll think about the person running on the staircase. These two people are doing different power, but they have the same work done. Work done is calculated by basically mg times vertical height for the both person. It will be the same. But since they are taking different time to climb it up, then they have different power. So that's the easiest way to understand the difference between power and the work done. Okay, so now this will be about the energy and the work energy principle and energy conservation, right? So now we're going to move into the next part, that is actually momentum and the collision and the momentum conservation. So now momentum also very specific quantity that we can define it as the conserved quantity, similar to the energy. But momentum is property of moving matter. We call it as the moment. What that means is, that means sometimes you need to consider the mass and velocity together. In that case, we are discussing about the momentum, especially when the players are playing football or any other balls that we know that we are talking about most of the time, or announcer most of the time use the word momentum. That means he's talking about mass and velocity together. So momentum is defined as mass time velocity. As soon as you write that, you will see mass is in kilogram and velocity is meters per second. Then this will be the units of the momentum. Right? Momentum is mass times velocity. Mass in kilograms, velocity is meters per second. But it is very important that momentum is a vector. Okay, now we need to again use the vector informations when you have the momentum, when you use the momentum concept. Direction we need to take account to your calculation. Okay, so now let's see if I have two balls, right? One ball and second ball. So if I move these two balls, if I have the first ball with the high speed, then they're going to collide and then going to move together or separately. It depends on what masses they have and also what are the initial velocities they have. Those are the things that we're going to discuss in this part, right? So now we will say I have a ball A, 1 kilogram and moving with 1 meters per second. And I have B ball, 1 kilogram again and 3 meters per second. So now if I calculate the momentum for A and momentum for B, those are different. Why these are different? Although they have 1 kilogram, they have different velocities. Because of that, they should have different momentum. So now we'll say I need to calculate the momentum of a ball. A I use for the A and I use for the initial. Initial means before collide. Okay. And then I have MA times VA for the A ball. Since both are moving in right direction in this case, although you think about the vector information, they are in same direction. That means positive direction, right? Both have positive momentum in this case. What is the negative momentum means? If the ball is moving backward direction, then that has the negative momentum that you need to consider it as negative for the calculation. So now here I have positive momentum for the A ball, MA times V. Now 1 kilograms times 1 meters per second give me 1 kilograms meter per second. And B ball, MB times VB. MB is 1 kilogram, 3 meters per second. I get the 3 kilogram meters per second. So now this is individual momentum. But how do you calculate momentum of the system is you have A and B together. Then you need to add them together. Then you have 4 kilogram meter per second. If they are moving in same direction, if one is going opposite direction, then you need to subtract that, not add. Okay, that's how we calculate the momentum of the system. Okay, as I mentioned earlier, also momentum also a conserved quantity. That means you can say initial momentum will be equal to final momentum. That is, we call it as momentum conservation. In formula that I will write, momentum initial will be equal to momentum final. But this is actually directional equation that you need to be careful. Okay. So now we'll say I have a before and after the collision example in this case, right? What is the momentum conservation means? Your A object has the momentum MA times VA, B object has the momentum MB times VB, but that is in opposite direction. This whole momentum initial, we call it as momentum of A object plus momentum of B object. So now if I write the initial momentum by choosing my X direction as positive, first object has the momentum MAVA, but second object I have negative momentum VB, right? So now when they come in head on, collide, and then we'll say they choose different directions. So now we'll say A use the backward direction, B use the forward direction. So now we have final condition. We are not consider this part yet, that is collision. Okay? So now P final will be equal to P A final plus P B final. So now in this case, what will happen is PA has the negative momentum MA times VA prime, new velocities they choose, but B has the positive momentum, right? So that's the initial and final. Then you're going to say this equal to this. That is the momentum conservation that we are using to solve the problem. Okay. So momentum conservation is very simple thing that you can easily use for simple problems that is in one dimension. But the collision can be different direction. In that case, we need to go to the advanced calculation. But for your case, conceptually, two balls hit, then what will happen to the velocity? You will be able to use the momentum conservation to solve that kind of problems. Okay. And last part I'm going to discuss is the collision and impulse. So collision is basically when two objects collide each other, we call it as the collision. Then they will create a force. This object will create the force on this object. This object will create the force on this object. What you can say about these two forces when they collide? According to Newton's third law, these two forces are equal and opposite, right? When they collide each other, they have the force equal and opposite. So now when they collide, we call it as, it will create an impulse. Impulse is not the force. Impulse is force time the distance that force act on the object. Simple example, you think that when you are playing the tennis, you have the racket and then tennis ball hit the racket in a few milliseconds, then ball will go backward, right? That millisecond amount, sometimes this force and time is you are not able to calculate separately, but you will be able to say them together. That is, we call it as the impulse, force times time. So force is in newtons, time is in second, unit for the impulse will be Newton second, right? But important thing is actually, this will be again able to calculate by using the momentum. So momentum, you know that if you calculate the change of momentum, that will be equal to impulse, right? That is another definition coming from Newton's second law that I will not going to derive it, but change in momentum in another way, we can call it as the impulse. Impulse will be force time distance, or it is change of momentum. Change of momentum, everybody know that when I write change of something, that will be final momentum minus initial momentum in this case. So now this has the momentum units. Momentum units, you remember that we call kilograms meters per second. So this unit actually equal to Newton second. Somebody can say momentum units is Newton second. Somebody can say momentum unit is kilogram meter per second. These two are actually equal. Impulse also have the same unit as momentum. Impulse will be able to calculate force time distance or change of momentum, but it's very important. Impulse we calculate for single object. Single object. And not calculating for the both. You know that if you calculating for the both, since they have equal and opposite forces, then your impulse will be zero. But we always calculate for a single object of the culture. Okay, so that's it for this section. Make sure that you attend the recitation and do the worksheet and also submit the homework on time.